We're here this afternoon at the University of Kent's School of Computer Science with Professor Michael Kölling. Michael is a member of CAS's board. He looks after CAS's website and also is the creator of the Greenfoot introductory programming environment for Java. And so we're going to be talking this afternoon about object-oriented programming, Java and Greenfoot. Right, Michael, thank you ever so much for having us here this afternoon. What is object-oriented programming?
Oh, now there's a big question. I've been trying to give people the answer for the last 20 years, and let's see whether I can do that in a minute or so.
Okay.
Object-oriented programming is one of the models of programming. About the object-oriented part is about how you structure your programming, and there are different ways how you can do this. Before object-oriented programming, there was structured programming, procedural programming, functional programming. It is essentially about, there are two different views of it, how you think about a problem and how you mentally organize your problem into smaller parts that you can then solve independently. And then that is reflected very directly also in how you structure your code, how you structure the program itself that reflects your thinking about the problem. So it's both a way of thinking about the world and about ultimately the programming problems you want to solve, and then directly reflected in code structure. And that goes through to characteristics of programming languages. So if you Python, Java, C++, the object-oriented programming languages all have constructs that help you to create the structures that fit in with that. And the term comes, the term objects is you start, in every problem you have, you can think about what is it that I have to do, or you can start as what are the things that I'm working with in this problem.
Okay.
And the object-oriented part is you start to think first about the things and then attach the actions to those things once you have them. So that's the objects, that's the object bit. Whereas in procedural programming, you first think about what are the actions that I have to perform. So if you have a sort of bookkeeping system, in a procedural way, you would think, I have to invoice, I have to add customers, I have to, you think about all the things you have to do, and you start structuring your program about all the actions that will happen. And in object-oriented programming, you start to think about the things, and you say, okay, I have accounts, I have invoices, I have customers, and that's your main structuring model. Right. And then you attach actions, or activities to those objects.
Okay, and we have this idea of objects and classes of objects.
Yes, that is the classes is just the general concept of a thing. So when I say, when we look around here, I say table. We can talk about tables, and often when I teach, I say table. Okay, what is that? A class or an object? And people take random guesses, and some say class, some say object, and then you can say, okay, what color is a table? And you can't quite answer that in general if the question is phrased by that.
Table,
yes, but if I say, what color is this table?
Yes.
Then you can answer that, because this table, that's an object.
Yes.
If I talk about tables in general, I'm talking about the class.
So returning to your bookkeeping example, all accounts have certain things in common, but
exactly. So
my particular bank account has particular properties to it.
Exactly. And then so you program the class account, which you program everything that's common to all accounts.
Yes.
And then you have concrete accounts, have 7 accounts, particular ones for particular, and these are objects. So once you program the class, you can create as many objects of those as you want. And so you can talk about classes. And that maps, it's not an not in a difficult concept. Sometimes people think, object orientation is much more difficult. It isn't actually. It happens all around us in the natural world that we deal with this quite naturally. We can talk about elephants without having an elephant in the room, and that's because we talk about the class. We're not talking about, I can tell you, roughly what they look like, what color they have, what their shape is, and these are all things. I'm talking about all elephants. The general idea of an elephant. I'm talking about the class. But when I'm looking at one particular old elephant in the zoo, that is one object, and there might be 3 elephants, so I have 3 objects.
So does this relate to the idea of abstraction in computational thinking?
Yes, very much. I mean, this programming in general is essentially about abstraction. Abstraction is probably the most important concept, and it manifests itself in many different ways in different programming languages. But the class-object distinction is one important example of abstraction that, if you have some objects in a program, that you don't program each of them individually,
right,
but you program the class so that you can sort of essentially program all of them together. Yeah. So if we have, let me show that with an example here.
Please.
Because one thing we do is teach object orientation with examples in Greenfoot, and just without explaining very much about Greenfoot, I'll just show you some little example here. So here I've got a crab, and what I see on the right here, this diagram shows me the classes in this project. And so I can create an object of this class crab.
Right.
So here I've got a diagram showing me the classes. Here now I have an object that is one particular one. And so if I start programming, this is if I run my program, it doesn't do anything because I haven't written any code yet. I can open the editor, I can write some code into it. And when I now go back and I create the object again, now it runs. So I have programmed. So the question here is, have I programmed the object or the class? What I have done here is I opened the class. And
this is rather different to how we would make a crab move across the screen in Scratch, where we would write a program for that particular sprite.
Exactly. That is one of the main differences. Even though Scratch and Greenfoot share a lot about sort of the approach to teaching, approach to programming, that is one significant difference, that Scratch is object-based. Greenfoot is class-based. In Scratch, you program individual sprites, they call them, the objects, and you program them all individually. And there's a clone function to make it easier.
Drag code from one sprite to another,
but still, you have to manage to get the code into each object. If you have only one object on screen, you don't. The difference doesn't become that clear, because you have one class, one object. Then it is actually confusing. So you see the difference really easily when you create more than one object. And so pedagogically, when we teach, we do that very early. We always make sure. So if I now create 3 crabs, and I run this, they all run around on screen.
Because they're all members of this same class.
Exactly, because I'm actually programming the class, and then the objects exhibit the behavior that I've programmed. So if I change this so that I say make them turn as well, and I've just put an error in here. So if I change my code and I put my 3 crabs back in and I run it now, they all do the same thing. And that is why these visual environments, such as Scratch and Greenfoot, are so helpful, because the difference between a class and an object is really difficult to understand if you always only stare at lines of code.
Of course.
So if you have an environment where the main part of the screen just shows you lines of source code, and you think in terms of lines of source code, just the question of, am I dealing with a class here or with an object, is quite confusing, and it's hard to understand, because it's actually both. If you think about the static work you're doing, the actual writing, you're actually editing the class. But you also constantly sort of imagine that running. You're thinking, what would this code do when I execute it, while you're programming? There you're actually thinking about objects, and you might have multiple. And so these environments that show you that visualize this, they help a lot. This difficult question, what's the difference between a class and an object? You almost don't have to talk about. That just goes away. People just see it, and it's not an issue anymore. And you can see it really well, the difference, if you have other examples. I've got an example here, for example, where I have an ant simulation. I have here 2 anthills, here and here, and now there are ants coming out, and they're running around. And you can hear that. It's an interesting example because it displays emergent behavior, where the actual behavior of the ants is quite simple. The program, their behavior is, what an ant does is just runs around completely randomly, and then when it happens to run into some food, it picks some of it up and runs straight back to the anthill.
Right.
And when it runs back to the anthill, it leaves these drops of pheromones. That's this sort of whitish cloud that you see here. And when another ant that is just running around randomly, when it smells some pheromones, it just turns away from the anthill and goes that direction.
Okay, right.
And if you get a single...
mirrors the biological situation very well.
It is a reasonably, slightly simplified, but reasonably good abstraction of what actually happens.
Yes,
and so if you've got a single...
state and behaviour of computational systems, as we talk about in the program.
Yes, exactly. Yes. And so if you've got a single ant that finds some food here, it will never make it back because these pheromones evaporate rather quickly. So it doesn't get back before But if you've got enough ants together, you see these stable trails forming because they constantly renew the pheromones. And the interesting thing here is that there is nothing at all in the code about forming paths. This path forming, no single ant knows anything about path forming. That's a behavior that emerges out of the system as a whole.
Out of the rules, yes.
And of course, these things are fascinating to play around with. And so they make good programming examples because you actually see something happening that you didn't really know. That's actually quite hard to predict.
Yes, we're using the computer to solve a problem that
Yes, and
we wouldn't be able to solve another way.
Exactly.
It would be really hard.
That is such a sort of sad thing about many programming examples used for beginners is that we make them do something that you would normally in real life never use a computer for. So when I started learning, you get this program the prime numbers or print out the prime numbers from 1 to 100.
Okay.
And the point is, first of all, if I really wanted to know the prime numbers, first of all, I'm probably quicker with a pen and paper and a calculator than writing a Java program for it. Or, in fact, the real answer is if I really wanted to know the prime numbers to 100, what you do?
I would Google it.
Exactly. You Google. It takes you 10 seconds and there's the answer.
And
so that's
persuading a student that it's worth programming if that's all that you're going to do.
That's the first problem. It's an artificial example that you would not normally do. And of course, once you solve it, once it prints it out, there is a buzz to it. There is a moment of sort of satisfaction when you prove to yourself that you can get it done. But it doesn't survive. It doesn't carry on. Once it's done it, there are two problems with it. First of all, what do you do next? You can print out the numbers to 200 or so. It's not interesting. There's no.
Why would I want to?
Why would I now want to continue with this? And the second problem is, you already knew all along what it would do. You're done when the program does exactly what you knew it would do. So you learn nothing new, but you learn something maybe about the programming, but you it has no purpose to tell you something else that you didn't know already.
But by modelling very simple rules of how an individual ant behaves, we learn something about how an ant colony might behave.
You can
in the real world.
Exactly. Yes. And you can, so even if you admit that this is not maybe accurate enough to make real, but you get a sense of how these things work, how you can do simulations that make predictions. And not only that, you can actually also observe behavior of your program that's very hard to predict. For example, I can say now, sort of popular exercise that we do with this is say, we introduce pollution to this, which has the effect that the ant can't smell that well anymore. So they have to be half the distance to the pheromone before they can smell it. Will they still be able to form paths or not? Now that's a question. It's actually very hard to answer theoretically, but easy to try out. So you go and program it and see what happens, see how it behaves. And so a lot of the behavior changes here. When you change the behavior of a single ant, of every ant, because you're programming the class, predicting the behavior of the system overall is sometimes quite difficult, and sometimes surprising things happen. And so that's why it's actually fun to play. But when I wrote this, I was sitting there all afternoon, playing with my ants, and it's just fascinating.
This would be very difficult not impossible, difficult to program in Scratch because of the need to modify the behavior of each individual
Exactly.
ant.
That's actually. I almost forgot my point there. That's the point I was trying to get to. That's why I brought that up when we started talking about the class. And because here, in what I just said before, object notation at the beginning of this conversation, every ant is an object. but also every pheromone is an object.
I was wondering about how granular the objects get.
So I can...
The ant is an object. The food is an object as well?
Yeah, the food is an object. The anthill is an object. In fact, he is a counter for the food. The counter is an object. The world itself is an object.
Okay.
Everything is an object.
And the pheromones.
And the pheromone. And in fact, here you've got the pheromone on screen. You can see I can just grab it and move it somewhere else. And you see here is my pheromone object. I can interact with it directly. In Greenfoot, I can take it, I can move it somewhere else, and can right-click on it. I can invoke a method on it, and so on. So these are all objects. So here, when the ant colonies are all, have all their ants out and they all leave pheromones, I have a few hundred objects on screen. And that would...
But a significantly smaller number of classes.
Exactly.
Yes.
So I have one ant class, but I have 50 ants or so. And doing that in Scratch would be difficult because, of course, you can write your ant and then you can clone it 50 times. But if you then decide to make a change, you decide, oh, my ant doesn't do quite what I want to do, then you're stuck. You have to make that change 50 times. So once you get into these sort of slightly larger problems, that's where Scratch reaches sort of its end. And that's actually a really nice point where to motivate educationally the switch out of Scratch and now to start with something like that.
I think that takes me on then to the next question. This is wonderful. Is this something we should be teaching in school, though?
I think so. I think there is there are enough general computational insights in programming in general, and for me at the moment the most suitable is object-oriented programming, that are worth learning for every child at school.
Right.
That goes to the point of, what is computationally possible? What can we do with computers? How does it work? How is it? How does a computer work? How does it do things? Of course, using Scratch at the beginning is fantastic. Scratch is a wonderful system, and you can start really early, and there is a lot you can learn with the system. But I think there are a few lessons, such as the abstraction, where it is useful to move out of Scratch and go a couple of steps further than you would, into a little bit more, sort of a bit more complexity, a bit more abstraction, a step further. I think this abstraction ability to understand abstraction over objects, abstraction over functions, abstraction is a very valuable just sort of mental ability that transfers also to mathematics, to physics, to, where I think it is a general thing that I would really like to see taught to every school, a school child.
To get to this computational thinking territory of ways of looking at problems, ways of understanding systems, some sort of coding experience such as that seems to be important.
Yes, it is. I think this computational thinking, if it is not connected to then some form of implementation, is hollow. I think computational thinking is important, but I think it needs to be concrete at some point as well. It needs it's another form of abstraction. If you only talk about it in theoretical terms, then it does not become clear enough. It is like talking about essays in English without ever writing or reading an essay.
There's a danger that it becomes merely some sort of critical thinking, generic problem-solving skill, without the power of computation to actually implement the solution, I suppose.
Yes, and I think this experience of writing some code and seeing it run, something I have written myself, something I have thought up and I have implemented, and then seeing it run, it is such a fundamental experience. No one who's not written any program can understand this. Everyone who has written a program understands what I'm talking about. There is this when you write these cryptic characters, or drag some blocks, whatever it may be, and then suddenly, and you click that button and suddenly it does what you wanted to do, or even it does something you didn't expect. It is such a joy. It's such an effect. Then you understand the power that you have.
You get much more of a buzz out of writing code that makes something happen than designing an algorithm which might do that.
And you really get this sort of godlike feeling where there is this universe in the machine which is completely sort of open and malleable, and you are the creator who can now decide and you have the power, and you can tell that people 10 times and they will not understand what it means until you've experienced it.
It's a visceral experience. Yes.
And so this whole computational thinking thing, which is so fashionable at the moment, I think is one...
It provides some justification for computing for all.
Exactly.
Yes.
And it is a useful and important thing, but I think it needs to be paired with actual concrete experience of building something. Because that is when people really understand the power of what they can do and where the joy comes from. You know, the joy does not come from theoretical concepts. And of course you can, the concrete form can also be unplugged activities. So there are some that are also fun, you know, but, and at young age, that might be the appropriate manifestation of it. At a bit older age, I think that though people should get their hands dirty and create some code.
Yes, writing a recipe for pizza only becomes fun if you get to make the pizza.
Yes, exactly. Exactly.
Yes, and writing an algorithm for, I don't know, sorting things or controlling an ant colony only really becomes interesting when you get to implement
and so I'm sort of part of a sort of maybe backlash now about this computational thinking, warning a bit to sort of not push it too far, because computational thinking has been used a lot and is sort of this buzzword to bring this in. And it's all true, you know, it's nothing wrong with it, but I have sort of my default position has become this warning to don't forget about also doing something concrete. And in computer science, that means programming. You know? It's not a replacement.
I'm reasonably persuaded of the argument that the best way to learn computational thinking is through programming computers. Is there evidence to support these statements, though? I mean, it seems plausible, but has anybody done the tests and seen who develops computational thinking better, those who program or those who don't?
I'm not aware of anyone who has investigated this. I mean, there's of course a lot of evidence, a lot of sort of anecdotal evidence and experience about the joy that people get out of programming. But I haven't seen a systematic study investigating whether you can develop that without
And the anecdotes coming up from school teachers are very much of the position that actually children seem to enjoy the coding an awful lot more than the theory lessons. And that shouldn't come as a surprise to anybody.
No, and I think we just have to work on cutting out the sort of painful, less useful elements of coding. So not everyone needs to become a professional programmer. You know, not everyone needs to program C++ in a professional environment. You know, that's not a goal for school age. So there are elements of programming which take it too far, which are not necessary to develop a fundamental understanding about computational principles. And that's pedagogically the challenge to divide that, you know, to say, well, what are the really useful principles and how can I present them as simple as possible, and what can I cut out, you know? And there's computing teachers debate a lot about syntax. Syntax is one of those things, you know, you can make statements both ways. Either it's not important at all or it's really important. It's conceptually not important at all because you learn little with it.
But it has to become something which is part of your ability to command the computer. Otherwise, it's a stumbling block, and you don't get to be expressive of creative ideas.
And that's exactly right.
Other programming environments which are not as demanding in terms of syntax are available.
That's right. You need the syntax. Syntax is important only because making something is important, and you need to get past it. But in itself, it has little value. So that's why we would prefer environments that keep the syntax hurdle low, because in itself it has little value. But it's
easier to concentrate on implementing an algorithm, solving a problem, if the syntax either comes automatically or is done automatically.
Exactly. And so it is, but it's important then, of course, to get everyone to a point where they can implement and create a program. And that sense. And so that's an area we have also worked on, where, of course, again, Scratch, we've mentioned that before, has one of its main strengths that the syntax is so simple that people perceive it as essentially syntax free, you know, where you cannot
never
have syntactical errors.
Syntax error.
And the snapping the blocks together technically is asyntax, but people have a lot less problem with that. And in Greenfoot,
I suppose that does take us on to Greenfoot, which you've already demonstrated. So how did it get started? What were you trying to do with Greenfoot?
We had another environment that we had before called BlueJ, where we were thinking about university students as our target group. Yeah. And then there was a time sort of in early in the century, around 2004, so we started thinking about it, where we became more and more interested in teaching at school level at a younger age. Because that's where all the action was. Yes. I was sitting here in my university and we were talking about teaching to beginners, but the beginners were actually out there in schools now. Yeah. And I've always claimed that I'm interested in making tools for beginning programmers. I thought, like, if I'm serious about beginners, I actually have to go down a bit lower into age. So we started thinking about a programming environment for school, and BlueJ had been used also in schools to a certain extent, but my feeling was that it's not actually the real right environment for it, especially when you talk about the whole population. In universities, we have the luxury that we have a selective audience. We have only people here who have in some way chosen to be here.
And been chosen to be here.
And being chosen, that's right. Not always with the exact motivation that we'd like to see. Sometimes their parents pushing them a bit, but by and large, they want to be here, they want to learn about programming. As a school teacher, you have a much, much harder job. It's a much more difficult position because you don't have that luxury. You have people sitting there, and for some subjects, they may not want to be there. You say, if you walk in and say, today we're doing programming, there are classrooms where half the class already has lost interest before you even start talking. There is such a strong prejudice against programming. It's not even well informed always. Sometimes it's pupils who have never done it still think they don't like it already. And so you have a very different battle. And so Greenfoot started with thinking about how can we design an environment that is very quickly motivating, where within the first 10 minutes I can show them something where they suddenly sit up and look and think, I want to do that.
Okay.
And that was much more important than the actual technical detail about whether we teach them every last little aspect about every programming concept. We wanted to draw them in.
Yes, because if a person is sufficiently literate and connected and motivated, they can learn so much more themselves.
Exactly.
The motivation
as a teacher
matters, doesn't it?
Yes. As a teacher, of course, once they want to know it, you can teach them anything.
Yes.
Instead of me sort of talking at them and trying to convince them why this if statement here is really important. If you can get them to put their hand up and say, how do I do this? Then you've won.
Yes, yes, of course.
And so that's the situation we wanted to create. So we start with very game-like scenarios.
Can you show us something? What would get potentially disenchanted year 8 people?
We've just seen so Greenfoot essentially is specialized to create programs where the output is two-dimensional graphics. So the ant simulation that we have just seen is an example, or I have another example here, which is an on-screen piano. If I run this, I can play this with my keyboard here. I've got the sound switched off at the moment, but I could put the sound on. So it doesn't have to be games. It can be anything where you have animated graphics, two-dimensional graphics on screen, interactive potentially. So that means often games, all sorts of 2D computer games you can do, or simulations, platform jumper games and animated games. And the way we start this is, I've just had shown you this thing with a crab where I started with very little code at all. You can either interact with these objects individually.
The scenario, the background, the crabs and so on are all provided there, and then we just write code for how classes operate.
That is pedagogically how we do it. It's not technically necessary. You can also create a scenario completely from scratch where you have no background, but we consider that an advanced exercise. So all the early exercises we give them, there is something there already. Typically there is a background of the world, so there's a world with a background, and there is at least one class, sometimes a few classes, that either...
Because spending time setting all of that up would detract from the object of the lesson.
It's not only the time, it is actually mentally quite, it's a harder exercise.
Yeah.
So when this question, what classes should I create? What are my objects? What are my classes? Or in a game even, what are my characters? Whatever, it's a design task that is actually conceptually much harder than the actual implementation task.
Yes.
If I say, well, I already have a crab and it has a move method, it just doesn't work, it doesn't do anything, just make it move. It's a much easier exercise than to say to someone, okay, what kind of game would you like to create today? And then if you have an idea, okay, what kind of classes do you need? Sometimes teachers are tempted to start with these things because in the development process they come first. But mentally, conceptually, they're much harder exercises. Pedagogically, they should come later. So we start small. We start giving them examples that already have a little bit implemented, where they just modify the behavior at first, and then they extend the behavior by just first adding a line or two to an existing method, then maybe adding a method to an existing class, later adding a class to an existing project. And at the end of it, after a few months, we let them start from scratch and say, okay, now we can make your own.
Yes.
So the fact that there's always something on screen is a pedagogical consideration. Technically, you can do whatever you like. But here I've got one where there's very little code. And this is in Java. That is, the programming in Greenfoot has traditionally always been Java. And we just have a very new version now where we also have a new language that I can show you in a minute.
Oh.
This is the old editor. We can now program in Java and in Stride, which is the name of the new language. I'll show you that in a minute.
Please.
So here I can, you get very quick turnaround. I can, for example, here when I let these run, they go in a circle. And if I now say, I want them to run in a larger circle, what do I change? And then I can say, okay, we do the parameter for the turn. We make that smaller. That's actually quite an interesting discussion to have with kids, that you have to make the angle smaller to get it larger. There's a first little bit of computational thinking where you can, where you can ask them, and if they're young enough and if they have trouble with that, you get someone to walk around, and do a step.
There's a nice unplugged activity, as well as getting at logical reasoning about thinking about the code rather than just changing numbers and seeing what happens.
Yes. So you can do that, and then now if I put my crabs in and they run in larger circles, so you see you have a very quick turnaround from editing the code and seeing the effect of it. It is very that's a sort of a nice early example that we can do.
And all of the heavy lifting of getting things to appear on screen and move in certain directions or in certain ways has been done for you in the scenarios.
That's what Greenfoot does for you. It does, you program just the logical state of the object. So I can say, I want my crab to move here. And the visualization and animation is what Greenfoot does automatically for you. So you just say, I've got another method where I just set the XY coordinate directly. So you can beam yourself somewhere else. I just say, I want to be at, XY 100, 100. And that's all you say. You don't write any graphics code. That's what Greenfoot gives you. So you just, if you say, I want to be there, you will see yourself being there. So that's the one of the contributions of Greenfoot framework, that it does the whole graphics thing for you without you ever having to think about this.
Which again illustrates our idea of abstraction, because that level of detail we don't need to worry about because clever people have done that for us already.
Yes. And that is why we prefer to start with an environment like Greenfoot. The programming language here being Java, there are many other Java environments or Python environments that are in language terms reasonably equivalent. But writing a interactive graphical program in a standard Java environment or in a standard Python environment is really, really hard. Graphics code is quite complicated, and they all make you write it. So the effect is you can't, at least not in your first year. And that is why we think environment is so important. It's not only the programming language that counts. If you think about what programming language should I use once I come out of Scratch, I want now a textual language. What should I do? Do I do Python or Java or C# or Visual Basic or whatever it may be? There is a whole list of possibilities. The one thing that often gets forgotten that I actually think is most important is look at what the environment is that you have available for it. I think the environment that you program in has a bigger impact than any difference between any of these languages.
That's interesting. Yes.
And for me, that actually would be my first criterion. It trumps difference between language, at least certainly between C#, Java, and Python, for example. They are conceptually so close that, whether you have a semicolon or whether you have curly braces or not, is a smaller difference than whether I program in idle or in Greenfoot.
The actual experience of where you're typing your code. Yes.
And that makes, for the student experience and learning experience, a vastly bigger difference than whether I have to type a semicolon at the end.
Interesting.
And so one thing I'd like to point out,
Please.
just because I would like to just, if I may, take a few minutes talking about Stride, because it's just our current research area. So that's the area I'm most excited about at the moment, because that's our new thing. And I can show you how we got there. We already had in our Java editor what we call scope coloring. So for example, if I put in an if statement, so I write some kind of if statement and I write a scope here, you can see this this box, this colored box appearing here. And I can write some code here, and it keeps the colors of, I'm writing nonsense now, but that doesn't matter. Having that scope matching, having the curly brackets matching and getting your scope right is one of the hardest beginners problems. When young programmers come out of scratch or have not programmed at all, and especially if they're young, if they're under 14 or so, that is actually quite hard to. And the most common error is that they delete a bracket at the end there accidentally, or because I don't know why it's there, and then they get cryptic error messages. So to help with this, we have introduced this coloring, which is sort of in real time. So if I remove that bracket here, that color shows me immediately sort of what the extent of the scope is at the moment. So if I have an error in there with my scope, it becomes much more obvious that it's wrong and where it's wrong.
Right. Yes, because things have to go in, or the place where things belong is a lot clearer this way. Yes.
So that was an attempt. This scope coloring was an attempt to provide some visual help with showing you the structure. But of course, because this is a textual language, you can still screw it up. You can still mess up the indentation. You can do it all, and students do. They have programs looking like this, and it still looks messy. So now, what we have done now, we have gone away from Java, and we have our own second language in Greenfoot. There's a similar program, and if I open the editor here, this is what it looks like. This is Stride now.
Okay, so Stride is not Java.
Stride is not Java, although it is a language that is quite similar to Java. It is a little bit different, but the main difference is not actually in the language constructs. The main difference is in the interactions of program manipulation. Technically, it's a different language because there are some differences where it is, but it is intentionally a language that is very similar to Java.
Once you've got good at programming in Stride, you'll be able to make the transition to Java very easy.
Yes, the object model is the same. All the language constructs.
The syntax of the grammar of the language, if not necessarily the interface of programming.
Yes, the whole object model is the same. The whole mental model is the same. So, and you see here are these colored boxes as we just saw it before. But now what I can do is I can take these and I can put them somewhere else.
Very nice.
So the statements in the editor have become first-class interface elements now. And so now I don't actually have to write them out anymore either. If I put my cursor here, this blue bar that you see here in the middle is our cursor. And if I want a while loop, I hit a single key and I get a while loop. So what we're doing here is we got a system that is halfway between blocks and text. And so we tried to see all the good things about block-based programming and all the good things about text-based programming, and thought, how many of those things could we get into a single system at the same time? And so, for example, we don't have half a statement anymore. You can't have this if statement with a missing bracket. We thought, why is it even possible in a modern system to have half a statement there? So here you either have an if statement or you don't. Just like in block-based systems. You know,
Yes.
you drag the block in or you don't.
Yes,
you
and
never
indeed,
half a
the
block.
compiler won't. It's not a valid statement in the language. The compiler
Yeah.
will throw an error message, but why should it even be possible to have typed the thing?
Yes, exactly.
Yes.
So here, if I put in an if statement here, I get an if statement. It's not complete. It's not syntactically correct because there is a condition missing, and so we don't do what Scratch does, that we fill in some default thing.
Interesting. Yeah.
So it's not syntactically entirely correct because we just have a field here where it says condition. You get a help here. It tells you there's a condition that you have to type in. But the condition is missing at the moment, so it's not syntactic. We don't avoid all syntax errors, but we avoid a large amount of the more trivial syntax errors. No more missing brackets, no more missing semicolons. No more unbalanced brackets. The presentation is also clearer if you have this colored block, and you can do a lot more. Now, for example, because they are syntax element, drag and drop, for example. In a text editor, you have to aim quite carefully to select the text, and then you drop it, and then you have to aim really carefully where you drop it. You can drop it in the middle of a keyword, for example.
Yes, I've done that.
There's no reason on earth why you would ever want to do that, or why you even are allowed to do this. And so if I take something here, I can drop it only where it's syntactically valid.
Yes.
I can, here it tells me, can't put it outside of the method, and here sort of in the middle of the keyword or the comment, you can't even get the target there. And so dragging your code around is much easier operation. You can just grab it and it will always be structurally correct. And we can also have a right click menu on them because it's an interface element. Of course, you have a context menu and you have some operations on there. I can, for example, delete the whole if statement, or I can have a delete outer frame that deletes the if statement but leaves the body there. So you can have, or I can disable it, which is the equivalent of commenting it out.
Right.
So you can suddenly do a lot more things. Or I can select some statements and hit my key for an if statement and surround them with an if statement. So there's suddenly a lot of editing operations become much quicker, much easier.
Yeah.
And a lot of the errors you make are going away. And then we have things, another advantage of block-based languages is this what in HCI, in interface design, is called recognition over recall, which is...
Right, because I can see all of the blocks there in front of me, and that reminds me.
You don't have to memorize them all. If you program in Python and Java, you just have to know what's there, and you have to type it in. You have to either know or you have to look it up, or someone needs
Which
to
you
type.
get eventually, but it takes a while to acquire that familiarity with
Whereas
the language.
in Scratch, you just poke around,
Yes.
Either you think,
For
I
good
have
or
this
ill.
vague memory, there was a block that does this, I can't remember quite what it was called, I can just search and probably think, oh yeah, it's that one. Or I can even think, well, see what else I can do, just look around and see, that looks interesting, let's try it out.
And this is why it's easier to use Windows and menu system than it is to work at the command line.
Exactly. And if you're a professional, that's fine.
Yeah.
But if you're sort of, a semi-frequent user, then it's a great help. And so we have here what we call the cheat sheet. We can that shows me all the statements that I have available and the keyboard shortcut to put it in. So if I want to know, how do I put in a for each loop, I can see that here. I can actually, if I want to, I can click on it and do that with the mouse. But the whole editor can be driven entirely keyboard based, so you don't have to touch the mouse. That's
Which
the
is
one
important
thing.
for accessibility as well. Yes.
Yes, it's accessibility, and it is this, going a step further towards proficient use.
Yeah.
Because no professional uses a block-based editor, and it's not because I don't know about them, but once you are well practiced and you know what you're doing, a text editor is actually much more convenient and quicker and can do a lot more. And part of that is that this drag and drop operation, great as it is for beginners, it gets tedious if you really know what you're doing. If you try to do Pythagoras or so in Scratch, you're dragging about 8 blocks into each other there, and you mentally you've already completed what you want to do, but the actual act of dragging it together, it's tedious. So this slowness, which is nice for beginners, becomes an impediment if you are a proficient programmer. And so we're trying to avoid that. So we can very quickly, here put something in one keystroke, and we get statement, and the expressions, if I have an expression, they are actually just typed in. So I can type very quickly a complex expression here. So you get the speed of a text system. In fact, slightly better than a text system, because you don't have to type all your statements out.
Yes, right. Yes.
But you get some of the error avoidance of block-based systems. And once you do something like this, let me open something that has a sort of slightly longer method. So just to show you that. So once you get away from the idea of that all code has to be raw text, once you accept that there's a combination of text and graphical elements, you can suddenly do things. This is just another example. That's a predator-prey simulation where the blue squares are foxes, the yellow squares are rabbits, and the foxes eat the rabbits, and so. But
it runs so quickly, though.
That's another advantage of another great motivator from moving out of Scratch into Greenfoot. It's just the performance. Once you have 1,000 objects, Scratch just isn't made for that.
I've attempted to program epidemic simulations in Scratch and give up at about 20 patients.
Yes, and in Greenfoot, because it runs on the standard Java virtual machine, it's a very professional, highly polished piece of software. We get really good performance. But I was about to talk about the editor. For example, there's lots of little goodies now that you can do. For example, when you have a longer method and you scroll up, often the method header gets out of view and you don't know where you are. And so here we just pin that to the top of the screen, and the body of the method goes underneath it. Or if you have a long control structure like this if statement, once the header goes out of screen, we just write the condition into the sidebar. And so you can do a lot of visual improvements over standard text editors. Once you get away from the idea that everything has to be raw text, or we do something where, let me go back. Oh no, I closed the other one. Okay, I'll just do that in here, it doesn't matter. If I put in, say, a method call, and I decide I want the turn method, it immediately tells me here what parameter I need. So it has put in the field for the parameter and tells me the name of the formal parameter. So if I put in set location instead. So I have here, it tells me here there's two parameters expected, X and Y. And so we can just show a lot more help than standard text editors can. So it really is sort of halfway between sort of blocks and text, where we get the really quick and easy editing of text editors with a good amount of the help that blocks editors provide, and in a single system. And then you talked before about transition to Java. If then people want to move on to Java, we have here a Java preview function that just then morphs this code into Java and shows you what it would look like as Java code.
So is that editable Java code?
Not at this stage. Okay. We have two functions. We have the Java preview, where you can go back and forth, but not edit.
Right.
Or we have a convert to Java, which then is editable, but you can't go back. The convert, once you convert it, because Stride actually, the scope is a subset of Java, we cannot convert all Java code to Stride.
Yeah.
So we can convert and have it editable, but then it's a one-way road.
Right, yes. Like we're saying from the Blockly to touch develop on the microbit, I think.
Yeah. So that is, and other systems like touch develop that you just mentioned, and various other systems are also at the moment looking at this blocks to text conversion point. It has become quite a difficult point for teachers, many teachers are very happy and comfortable in Scratch or other block-based language touch development, these because they are so easy to pick up. But then teaching in a standard text-based language, of course, is much more challenging for teachers, especially if they don't have a computer science background. It's actually quite a hard ask. It's quite a. I always thought, asking teachers to suddenly teach that if they don't have a computer science background, it's a steep challenge. It takes courage, I think, for a teacher.
Yes, yes. Picking up the language itself is one thing, but then teaching it to others.
Yes, and so that
have those
point,
years of experience.
exactly.
Yes.
So I think teachers should get all the help they can get at that point, and that point of going, when you make the transition, is a difficult point.
Right.
And the effect of it is sometimes that I think that block-based languages are used a little bit too long because teachers are worried to make this step.
Yes, and we are hearing stories from those teaching year 7 of children being really bored by Scratch because they've done it for 4 or 5 years in primary school.
Exactly. Yes. And so Scratch, nice as it is, if you've already done it for 3 years, then maybe it's time to do something else. And because the step to a traditional text-based editor is quite a big step, we wanted something that makes that transition easier. Yes. And we're not the only ones. There are a lot of groups working on it, but the solution that the other systems have is quite different. The solution in just about every other system I've seen is to show blocks and text side by side.
Yes.
Or let you switch back and forth. And sometimes in some systems, like pencil coder, so you can even edit either side and go back, and at least as long as you don't have a syntax error, you can go back and forth. So you have this 2 different views. You have the block view and the text view, and you can switch. But it's going to take a well-motivated child to move away from the block view there, isn't it? Yes. And at the moment, as far as I know, there isn't really evidence how well that's working pedagogically. It's too new. There aren't really studies. But the assumption is that somehow helps you. And that may be true, but I thought we can do a bit better than that. I didn't want 2 different views. I wanted a single system that has the good characteristics from both in a single system, not in 2 views, but a single representation.
And makes the subsequent transition to, if you'll allow me, proper text-based coding, a much easier one.
Exactly. First of all, if you then transition to standard Java, it's easier. And secondly, you may not need to, because there I see 2 different user groups. The ones who want to do more programming and maybe become programmers or have that as a hobby or so, they will want to move on to a standard language, Python or Java. So in our system, it's Java that we're leading into. For them, makes that step easier. But also, the general population, those who are not interested in becoming programmers, they don't need anything else. In Stride, you can present every programming concept that I'm interested in talking about. It's just the syntax that's cut out, just the bit that is boring. So all the talk about computational thinking and abstractions and programming and power, you can do that all in Stride. And for those people who don't want to go further, you don't need any more. It can that can be the end point where I think, I said at the beginning, I think Scratch is not quite enough. There are some concepts that I would like to discuss that are hard to illustrate in Scratch. Right. I think a language like Stride, that's computation equivalent to Java or Python. It's a full programming language. Okay. Yeah. It's just the edit interactions are different.
2 questions then. Firstly, what are the things that one can't teach through a Scratch-like environment that you can teach through Stride?
I think one of the important things we've already mentioned before, the fact that it's object-based and not class-based, for example.
Okay. Which is down to Scratch as a language rather than necessarily the block-based approach, or is it impossible to do?
No, it's not impossible, but and there are some block languages that are class-based, Alice, for example.
Oh, yes.
It is possible, but typically, so the answer would be slightly different depending on which concrete environment you look at.
Okay.
But they are all sort of limited in some way, in some, and they are just sort of abstraction techniques that are important to me.
But it's moving to a general purpose language, which Stride allows you to do.
Yes. So in every sort of traditional programming language, what is important for me as a teacher or as a someone want to teach about computer science is, if you have a programming language, you are not only a user of a language, you're also a creator of language. By making a new procedure or new method, you are extending your vocabulary.
Yes.
You're essentially you're making, and that is a very important moment of abstraction where I say, I have these, and the fact that in the older Scratch, before Scratch 2, that I think was a severe limitation, that you could not make your own blocks, because there it's you could just use what you've been given.
And you can, considering its heritage with Logo, when Papert was so eloquent about the importance of being able to teach the computer a new word, as he put it.
Yes, exactly.
The absence of functions and procedures from the original Scratch seemed very odd.
Yes, it is. And at the moment in Scratch 2, it is better. But it's still limited.
Very limited. Yes.
And so that's an important concept. I think at the age, if you teach in primary school, that's fine. I have no problem with Scratch. Well, you could use Snap instead, where that's a bit different, or some other. But things like this, where I think there is a very good justification for not supporting that in an early system. So I think in Scratch, it's not missing because the designer aren't aware of it or they haven't thought about it. It's a very well considered decision,
yes.
and entirely defensible. At that level, that is probably the right decision. But still, afterwards, that's something I still want to get to, where you, especially sort of in object-oriented programming, often instead of if here you've got a specification of a problem, the way you solve it is not always from the top, from the specification, but by building up a language, a custom language in the problem domain that allows you to talk about your problem. So this creation of methods in the problem domain is essentially you are creating a custom language that allows you to express your problem well. And there are fundamental ideas of computation and abstraction in there, where you need to go beyond these block-based systems.
Okay, fine. My second question, do you think we will see these sorts of features coming into more mainstream text editors?
I certainly hope so, and I cannot see any reason why we wouldn't.
Yeah.
This editing technology, we call it frame-based editing, that is implemented in the Stride editor. So frame-based editing, it's possible to create an editor like that for any structured language, any programming language or XML. They will, so I said before, they sit in the middle between blocks and text. They will not replace blocks. Blocks still have many reasons why you would want them first. They could, however, replace text. I see no reason, if there was a good implementation of a frame-based editor in your favorite IDE, why you would ever want to use text again. For beginners, it's easier, and the way when we talk about education, we motivate it as of coming from blocks, but sometimes we give talks at professional programming conferences, then we present it quite differently. You don't have to talk about education. There are advantages for professional programmers here. And it's a bit of a sort of dangerous field to move in sort of the tool designer, professional tool designer community, because this is actually an instantiation of what used to be called structure editors. There was a phase sort of in the late 80s, early 90s, where structure editors were very fashionable, and many were built with very similar ideas, and they spectacularly failed. And everyone who was around at the time and has programmed at the time, when they hear the word structure editor, they get goosebumps of horror, because they were awful. They tried to help you, but they were so restrictive. It was constant frustration to program in this. So it's always, you have to be very careful when you talk.
Wizard approach to spreadsheet design.
So you have to be very careful when you talk to professional programmers. If they get the thought and say, "Oh, that's another structure editor," you have a very hard argument in front of you and say,
"Interesting."
And where we're trying to say, yes, it is, but it's better.
Yeah.
And it's still a question of whether we really managed now to avoid the problems that made it fail the first time around. I think we have, but we have no evidence of that at the moment. It's too fresh. We only released it a few months ago.
Okay.
And there's a small number of teachers using it now. But in principle, I very much hope that it will go into professional tools as well.